So the recording has been started, and let me share my screen. So can you see my screen?
Yes, sir.
Okay. So I think while solving the week 1 assignment, you have found, I think, a few. Did you find some answers not matching with your with the final answers that is given there, or did you get all the things correct?
No, sir. I had some wrong answer. So,
Okay, so we'll do that one by one. Actually, what is going to happen at the end, that if you opt for the exam is there. Actually, for the final exam, mostly the similar concepts, and whatever the questions are given in the assignments or quiz, the similar type of, the same question will not be there obviously, but the similar type of questions or the concept will be asked from the similar thing. So it will be good if you can solve the assignment. So that is the whole idea behind this PMRF session and the other thing. Okay, whatever. So let us start. So this thing you already know that we'll get this recorded version. I think this is already available. The first lecture what we have done. Anyway, so we'll always start with the electromagnetic spectrum for this course, because this is a very important diagram, or you can say this is the spectrum which we are going to learn about. Means radio waves, longer wavelength, and the gamma is the shorter wavelength but the higher energy. So this thing you know, but you don't have to remember the thing, but you have to get an idea that we generally work on the visible region. We can see the visible region. Infrared is actually the vibe. So the previous day we were talking about the different energy levels, right? So mainly the electronic energy levels, the fluorescence, those part comes between this visible region, and infrared region, IR region generally deals with. So as you can see, the energy of the IR region is less, but the wavelength is more. Okay, so this region less energy than the visible region. So this is the vibronic energy levels. So to deal with the vibronic energy levels, this infrared spectroscopy is there. And today we'll going to actually week 2 actually focuses on rotational spectroscopy, that actually deals with the microwave spectrum. Okay, so and that has even lesser energy than the infrared region. So first we will solve the week 1 assignment, and then we will discuss some of week 2's maybe formula you can say, or if you have any doubt. I remember that I didn't share the Seebeck effect some document, so I'll do that. I'm very sorry that I could not do that. I'll do that as soon as possible. So let us start with the week 1 assignments. So I'll read out the question. You can see my screen, right? And you let me know what is the answer, and then we'll try to solve it together. So the question is absorbance of a sample S, and the sample is S, at excitation wavelength is 0.1. So intensity of emission is 1000 units. So what are the things given? I am writing here. So absorbance is given, A is given, A for the sample is given, that is 0.1. I emission of sample is given, that is 1000 units under the identical conditions. So for quantum field with respect to the reference, so one part was very important, that the conditions should be identical. So we under identical conditions, intensity of the a standard reference, that is the emission quantum yield, means the quantum yield of that standard, that is phi f of the so here we are denoting S for sample the reference. Okay, that is the standard solution. So reference is given that is 0.5. That is, you don't have to know how they have got it, or may have they have done absolute quantum field. That is a different thing. So let us not go to that. So this is an standard quantum field of the reference, and that is given. And at the identical condition, they got that absorbance of that reference. The concentration may not be the same. The concentration of sample and reference may not be the same. So what they are saying, that with the identical condition, using the same machine at the same time, what they have got, that they have got an absorbance of 0.05 for the reference. Okay, and they have got a reference emission, they have got 2000 units. And let me write it also units. So in physical chemistry, units play a great role. Here unit means arbitrary unit. Unit can be anything. Means I am saying in general, whenever you are going to do mathematics in this course also, the rotational spectroscopy is going to come. We will discuss some of these week 2 assignments also. So you will see the unit play a major role. So you can't miss out on units. So you need to be very careful. And you already know that absorbance doesn't have any unit, right? So let us solve this. You know that phi f of a sample would be, can you tell me what should it be? I emission of that sample, whatever the photon being emitted by the photon being absorbed, right? Is absorbed, and it can be written in another form, that is I sample emission, intensity of that, and intensity of absorbance, that can be written in terms of I0, that is the incident intensity of the incident light for incident on the sample, 1 minus 10 to the power minus absorbance value. I think you know this, right? I think this has been shown how you are getting. Do you want me to do this, or it is fine for you, Avantika?
No, it's fine.
It's fine. Okay. So did you use the similar concept to solve this? I hope so.
Yes, I actually use that pi emission as divided by pi emission R.
Okay, okay, very good. So those who will see this thing in internet or YouTube, maybe I will just do this quickly so that you are here. So this is also I reference emission by I naught. So this I naught is common. So let me write this 10 a sample for this, and 1 minus 10 to the power minus a reference for this. So what we are trying to get, so I0 and I0 are common, right? So under identical conditions, same machine, right? So what I am going to do, I am going to take a ratio of this, and what I will get, that I sample emission by 1 minus 10 to the power minus as into, and the same thing I will get here, 1 minus 10 to the power minus absorbance reference by I intensity coming emitted right from the this, right? So this is eventually is all the things I think are given right now. So 1000 by 1 minus 10 to the power minus 0.1 1 minus 10 to the power minus 0.05 by 2000, right? So it will be, so I don't have any calculator with me, so can you do that calculation for me, or I will use my phone?
The answer comes out to be 0.13.
0.13.
13.
So almost close to, so something will come and it will be equals to 0.13. Okay, So the first will be the answer, right?
Yes.
Hmm?
Yes. Yes.
Yes, right. 1 1 3 1 2 5 are the almost same, right? 1 2 5. So I guess you are giving. So this is going to be the correct answer, right? Actually, let me check also. So okay, let me do the calculation quickly. 1 minus 10 to the power 0.05 divided by 1 minus 10 to the power minus 0.1. That is coming. Why this is coming negative? Achha, this is coming to be point. I think we have done some mistake. We are getting 0.53 here. 0.53. So 53 if we getting 1 minus 0.1, then divided by 2, that would be 0.264. So actually not 0.13, it will be 0.26 something. Is it that 0.26 or am I making any mistake?
I think it's first one. 0.125. Answer, correct answer.
Is given the correct answer, right? But is it the correct answer? I mean, I told you that there is some mistake in some question. I don't exactly remember. So, acha, I will do this once more. The calculation. 10 to the power minus 0.05. So actually this is going to be total 0.109, and if I get this one, then this is 0.2. This is coming to be 0.2, 0.205 whatever. So actually this is 1 into 0.1 and 0.2 into 2. It is 1/4. Actually 1/4 means almost 25% or 0.25. Actually the correct answer would be 0.250, not 125. Is it given the correct answer? You are saying it is given as the correct answer. Let me see also. Maybe the answer that is given, that is wrong. It could be. Sometimes it is something like that. Okay, the answer given is 0.125. I think the answer given is wrong. But when did you solve it? How much did you get? Do you remember?
Mm.
Hmm?
Yeah, just a minute.
Okay.
Yes. You haven't multiplied it with 0.5 now?
Oh yeah. Yes.
Mm.
Okay. So I am very sorry. So the thing is, what we have got, that phi SF is equals to phi RF, right? That I have missed. That is equal to 0.25. Yes, you are correct. 0.5 into 0.25. Now I think it's clear. 0.5 into 0.25. So it is coming as 0.125. Yeah, you are correct. Great. I am going to make some mistake like this. I am very sorry. So this is correct. Okay. So I guess you have done this then, right? So that's very good. So what I told yesterday, that actually this is the thing when you do the thing in the similar under same condition, and that also means you are taking the same solvents if you are doing in solution. Okay. So but if you are going to do in different solution, I mean suppose your sample is in a different solution, suppose your sample is in ethanol but your reference is in water, then another factor comes in, that is the refractive index. So that is of, suppose the solvent you are using for sample and square of the refractive index of the reference that is in the solvent. That part usually comes in when you don't use the similar solvent. Okay, very good. We have done this thing right now. I guess this is correct. So can we move to the next question then?
Yes.
Okay. So the next question is also based upon a mathematical formula that has been solved using the Michelson interferometer. So where the velocity Vm of the mirror is given 1 meter per second inverse. So we have to be very careful. The signal on this interferometer for light with wave number 1000 centimeter inverse. So let me remember the formula. I also don't remember. So what I can remember, that velocity of that multiplied by the time will give you lambda by 2 is the distance covered by mirror, right? Is it something like that? Yes. So distance covered by mirror for a, I think, constructive interference. So that gives us Vm, lambda. So that gives us Vm. Tau is 1 upon frequency, right? Frequency of the signal, and tau is the time taken to cover this distance. So frequency of the signal f signal is equal to 1 by tau. So you are eventually going to get from here lambda by 2, and your lambda is 1 upon mu bar, right? 2 mu bar, or the wave number. So what are the things we have here? We have the wave number of the light, means that is we have the velocity, we have the frequency of the signal. Okay, so let us write. So Vm is given 1 meter second inverse divided by the f signal, that is also given 10 to the power x, okay, is equal to lambda by 2 or 2 into 1000 centimeter inverse. That is very important, centimeter inverse. And this is actually 1 meter per second inverse, that is 100 centimeter. So 10 to the power x going to be 2 into 1000 centimeter inverse multiplied by 100 centimeter means in second inverse. And it is in Hertz, right? Hertz means second inverse. So second inverse is here. So second inverse gone, centimeter gone. So means it is on the order of some 10 frequency, so it could be n into 10 to the power x or something like that. So where n can be 2, right? So actually 10 to the power x, that is 2 into 10 to the power 5, you can see, right? So actually your x is 5, but your answer is given as 6 or 4. It is, I think, given as 4 maybe, right? But actually means you can see the 5 is not here. Actually I remember the question is set as a fill in the blanks question, okay, and the right answer was 5, and for that actually the range of right answer was given that 4 to 6, okay. So I think later the question has been changed in a MCQ type question, and the options that they have given is not correct. Are you getting my point? Did you did you
Yes.
did you get 5 or did you get 4 or 6, something like that?
Yeah, I got 5.
Okay,
But actually, my classmates, when they did this question, they used log and something. They used log and then they got the answer.
okay,
So, and some got 4 and some got 6. So,
okay. So actually the answer is going to be 5. It's no, you don't have to use log and other things. This is the formula, easy formula what you can use. Okay. Actually the answer is going to be 5. Actually the answer was 4, given in the range between 4 to 6. Maybe someone who didn't understand the question may have changed the question in such a manner. That's why the thing has been done. So this way, so whatever mistakes is there in the question, and suppose you are putting 4, or suppose you got 5, so you have gone for the 6. So don't worry. In the so these all will be rechecked, this question, or so whatever question you have already answered. So for if you have attempted, you will get marks for that question. Okay, at the end. For the assignments, actually will carry some marks, I think, for the course. So even if it such is the course, we will you will get the marks, everyone who have attempted. Okay, so let us so if this is clear, so we can go to the next question then, right?
yes.
Yes.
Yes, so go to the next question.
Okay. Okay. So the unit of the absorbance, that is, though we already know, because it is absorbance is a logarithmic thing, and obviously there is a ratio and of that, and that's why it is there is no unit. You will see in certain papers or in certain um, publication, there is unit is written as AU, that is the arbitrary unit, okay, but that is actually not correct, okay. So that you have to know. So unit of absorbance, there is no unit of absorbance, okay. You can multiply with some other physical parameters, then the unit will change, but that then it will not be absorbance, right? So like from absorbance is equal to epsilon CL, right? So you can plot instead of absorbance. So we generally frequency domain, we already seen that we plot it like that. So in some publication or in somewhere you may see that they have plotted epsilons against lambda. So that is the same thing. So what they have done, they have divided by CL, right? Now epsilon has an unit, so that can have an unit, but absorbance doesn't have unit. Okay. So the next question is very important. So the resolution of Michelson interferometers depend on, what do you think? So the 4 option is maximum length traveled by the moving mirror, speed of the moving mirror, degree of the monochromosity of the light, incident light, or reflectivity of the optics involved. What do you think?
Basically, first one, the maximum length traveled by the moving.
Maximum length. It has been taught, right? But I think in the
Yes.
correct answer it is given at speed of the moving light, because Sir was mentioning something like this, right? It is going, so it will form an pattern like this. So more the point, more So if the speed of less, then more points will be there. But it is also true, the speed of the moving mirror does play a role, but obviously the main thing will, the lengthier thing with the more data we'll get. This is in time domain, right? This is in time domain. So whatever we are getting, so this is in time domain. So whatever will be from FTIR using Fourier transform. If Fourier transform, we will get something. So suppose here I am showing one frequency, right? So you should get something like this, nu bar, and suppose P of nu, something like that. So you are getting only one frequency, something like that. So more, suppose, so this is an interferogram, something like this, something like this. So you will get something spectral like. So you need more frequency. So that will be more clear when the maximum. So light will be traveling the maximum length. Okay, you are getting this. So we will not discuss this more. So let us go to question number 5. So this is the right answer, and the question number 5 is resolution of a scanning frequency domain absorption spectrum depends upon. This is another important question. So this has been discussed, I think, during the resolution part. What do you think? So one more thing. So the round options will let you know that this is a means only one option is correct. This is a MCQ, and this is a MSQ type question when the square type options are coming, and these are MCQs. Okay, so there are multiple correct answer. Automatically when you see the square type thing, you will understand this is a MSQ thing. Okay, so what do you think? Yes, you were telling something.
Yeah, the answer I chose was first, second, and fourth, but the answer is first and second. So
Yeah, so you chose intensity of the incident light as well as and the detector as well as, right?
no, first, second, and then fourth detector.
Okay. So the slit width you correctly choose because suppose from the final mirror, two wavelengths are coming, something like this. So I am not putting it a different color. That actually is true, right? If you choose the slit width to be small, then only one wavelength will pass through, right? Lambda 1, and suppose this is lambda 2. So lambda 2 will be blocked. So that is correct. Now quality of the grating. So that means the how much spacing is there in between each grating, right? So more the number, more the number of grating, or the less the spacing between the lines. So D smaller, actually that will lead to high resolution, right? Means it will means the more the resolution in lambda will be high. So the D smaller means the quality of the grating. So that is also an important part. Now intensity of the incident light obviously plays a role. Suppose that is very less, so this is not coming, but suppose high intensity and low intensity. So what do you think? If grating is suppose there is high resolution grating, means your quality of grating is high, and the slit width is also less. So do you think what will happen with if you increase your intensity or decrease your intensity?
Well, it won't matter because the slit width we have to choose now. So
Yes, actually yes. So that actually deals intensity of the incident light, that actually deals with the your light gaining power, something like LGP. I think that has been discussed, but that is not really the resolution thing. And what do you think about detector? So suppose I am using single photon detector, SPD, not SPAD. So that is a different thing. Suppose this is single photon diode, means it can we have to scan the grating for this. We don't the detector is in place, and another is suppose array type of detector. So there are multiple spots are there. So multiple like CCD, charge coupled detector, something like that. So do you think what does it really play a major role in resolution? What do you think? Anyway, we are scanning the grating.
I think because in single point detector, you are mirroring the wavelength one by one, detecting it.
Yes.
So it will the resolution will be more in this case, no?
Yes, resolution will be more, but the thing is the time taken will be high. So actually, the detector will to have to deal with the time, right? How much scanning we are doing, right? It not so if the CCD detector is there, I think Sir has discussed that if more light falls into it, so the resolution is not that good. So the resolution will be good when the megapixels, that kind means more the number of arrays, the more will be the resolution. So actually that doesn't, obviously if it is a more megapixel camera, something like that detector, so it will be good resolution. But for SPD or CCD, actually it won't affect that much with the resolution. So the main thing that is going to affect your resolution, you are correct, that one is slit width, another is quality of the grating. So detector and incident of the light, that doesn't really it has some effect, but it is not the main thing in resolution. Okay, so these are the two, slit width and quality of the grating. And SPD, so single photodiode, that actually will take you much more time to get the data, and CCD will give you quickly, because here the scanning is not that important. So you can have a big slit, right? So that these lambda 1 and lambda 2 will fall into different arrays. Okay, but actually you will see that actually depends how much light or what is the diffraction. I mean, suppose you are using a 600 nanometer incident light. Okay, so actually that is going to fall upon a 300 nanometer. The resolution is for lambda by 2, there is something called Abbe's limit. That is actually, he also deal with the resolution. So if it actually tells, suppose you are using a lambda nanometer light, so your maximum resolution would be something like lambda by 2, or you can't really detect 2 points if the distance is this. Means you can't really pinpoint these are two different points if the distance is lambda by 2 and the incident light is lambda. So for suppose 600 nanometer light, the means if the distance between 2 points are more than 300 nanometer, more than 300, then you can detect those points, or then it will be good. But if it is less than 300 nanometer or something like that, then there will be problem. Okay, so so instead of 2 points, you will see it something like this or something like this. Okay, so you can't really the resolution is not really good. That is in terms of microscopy I am saying, but it plays the similar role. I think Sarah's discussed something like that, right? Okay, I think we can go to the next question, right? Question number 6. Quantum yield of a sample recorded using a fluorometer depends upon, there are 4 options again: slit width, quality of the grating, intensity of the incident light, and sample. So what do you think?
6.
Yeah,
Second option.
quality of the grating. Suppose I am telling you, acha, why do you think quality of the grating is important for quantum yield?
I I moved on to the seventh question. I forgot the sixth one. Sorry.
Okay. For the question number 6, what do you think?
Depends on the sample.
Yes, it will depend on the sample to sample, because all the other things will be identical, right? These you have to keep identical condition. So these will all be same for the next, means the experiment with your sample as well as your reference. Okay, this is very easy. So for 7th one, there is again some mathematics. So what they are saying, suppose there are 2 samples mixture, where A is there, B is there, light of wavelength 300 and 500 means there are, suppose the absorbance is something like this here, okay, something like this. This is for A and this is for B, and this falls at 300 nanometer and this falls at 500. Let me also give this lambda and this as absorbance, right? So A absorbance sometimes you can see is OD, that is optical density, something that can, anything can be written. So absorbance of A at this point, or this epsilon, this lambda actually depends on, so what is that? Absorbance of A is epsilon A C of A, and path length is same, right? You are using the same cuvette, so path length is same. What is the absorbance of B? Suppose at 300 nanometer this is given 300, so your epsilon is also dependent upon the lambda, right? And for B also it is 600 500 nanometer, right? Oh, I'm sorry. B also at 500 nanometer there is some absorbance, so that is epsilon B at 500, and also it will depend how much concentration is there, and the path length is same. So we can do a ratio thing and we will get the thing. So we need the absorbance coefficient, right? That is epsilon A and epsilon B, also known as molar absorptivity, right? So what is also given, that the ratio of the absorbance, okay, good, absorbance A at 300 by absorbance of B at 500, that is given as 1 by 3, right? And what we can write here, so epsilon A at 300 nanometer into C, concentration of A. I am cutting the L from the both side because that is same. So 500 and C of B, that is actually we are getting 1 by 3, and the concentration is also given. The concentration A is twice that of B, that means CB if we cut we will get a factor of 2 here. So ultimately epsilon A 300 is to epsilon B at 500. So always remember the epsilon is a function of lambda. So what you are getting, am I making this correct? I hope so. So the absorber, what is the ratio between them? So the ratio is 1 by 6, right? Or 6 is to 1, right?
Yes.
Yes, so 6 is the correct answer. Okay, so I think this will test your knowledge from the week 1. So before solving week 2, we will discuss a little bit about the things discussed, so that we will get the formulas correct and we will go to the week 2 assignment. Okay, we will solve the week 2 assignment today only, so that we don't lag behind. Okay, so what do we have? Rigid rotor, non-rigid rotor, right? So I will only discuss the important formulas and the mathematical problem that can come from there. So you already know, for a non-rigid rotor actually it will have a wave function, something like this is the spherical harmonics, y depends on theta and phi. Why I am not writing the radial part? Because radial part is constant. There is some J and M, that is in terms of hydrogen atom, this is azimuthal quantum number and this is magnetic quantum number, right? But here for rigid rotor it will be different. Now what else is there? There is a Legendre polynomial is there, right? That is something like this, and that is on cos theta, that is a function of cos theta. And what else is there? There is that phi dependent part is there, that is e to the power I capital M phi. So in hydrogen atom we generally write, instead of in each atom we'll take this small l, we take it small l, okay. But in case of non-rigid rotor, this is the Schrodinger means a solution of the Schrodinger equation. So from here actually what you will get, the angular momentum, that is important, that L square. So always for operator don't forget to write this theta and phi. From here you get j into j plus 1, okay. So this is rotational quantum number, okay, for here. Am I stating it correctly? Rotational quantum number. Just correct me, huh? Whenever I am making any mistake. J into j plus 1. What is there? H Cartesian square is there, and it is an eigen value equation, right? So it will be like this. And what is the energy of any state? From the Schrodinger equation it will come from, actually we will see that the energy is actually L square, the orbital angular momentum. This is angular momentum, let me write it like that, angular momentum, L square by 2I. I is moment of inertia, and it will eventually give you H Cartesian square j into j plus 1 2 into mu r naught square. So here you already know that, so there are two body problem. Suppose one is bigger.
Is it for rigid rotor?
Yes, this is for a rigid rotor, where this is the distance. Suppose this is r0, distance between two things. So you, from a two body problem, so you need to simplify using the center of mass. Actually using center of mass, actually you are putting it as a one body problem, where your that point is revolving around a massless center. It is very important, massless center, okay. And the radius of this is actually the radius of gyration, and that is actually nothing but the, for a two body problem, it is nothing but the distance between two things, that is r naught. So eventually it become very easy. Means this will all comes from if you need to read the Manuel book. I think it is a little bit there, you can understand there. And actually this energy actually is in joules, okay. So I can write it in this term also, H Cartesian square j into j plus 1 8 pi square mu r naught square joules or j. But you will see in spectrum actually we will talk in centimeter inverse, okay. So these are the things I think in taught, I think I am repeating. This is actually going to be h j into j plus 1. So I am writing here because it will be easy for me and you to remember what is the rotational constant b and those kind of things, right? 8 pi square mu r naught square, c will come, and the unit will be changed to centimeter inverse, and it is nothing but b. This part is rotational constant. H you know, Planck's constant, 8 pi square is known. For a molecule you will know so mu is reduced mass. Do you know this? What is a reduced mass? So
Yes.
okay, so the reduced mass is nothing but the reciprocal of your these two bodies mass. So actually is a rigid rotor. So actually two body problem. So one having mass m a and m b. Suppose here I have written m1 m2 whatever. So this is actually your mu is going to be m1 m2 by m1 plus m2 I guess. Okay, so this and r naught for a rigid rotor, r naught is constant. C is the speed of light in vacuum, that is constant. So this actually is a rotational constant for a molecule. So for different molecule, rotational constant will be different. Okay, so this has to do with the isotopic thing also. So if you choose suppose nitrogen, two nitrogen atoms, right? 3 bonds are there. So if you choose 14 and 15 nitrogen with a 14 nitrogen, if some isotopic abundance is such like that, your nitrogen has something like this, so they will have different mu's, right? Means the reduced mass will be different. So for a particular thing, suppose 14n or 15n or for a 15n 14n, for eventually for a particular case mu is constant, what I am trying to say, and r0 is we are taking is as a constant for a non-rigid rotor. So you will eventually see nothing is a non-rigid, so there will be some terms will come. So that is a case for another time. And so this is the expression of energy in terms of centimeter inverse. You tell me, so then I will only discuss or I will not discuss. So eventually I am repeating the things, so I will not try to not do that. So did you understand the selection rule? How did it come? So the selection rule is delta J, right? And B, let me write is one, the rotational constant. So most of the mathematical problem will come from this equation. And another I have not written, delta E. So delta J, you will see this is plus minus 1. So let me write it like that. So delta E is the energy difference between J plus 1 to J, right? Or you can take it J minus J, energy of J minus energy of J minus 1. So this actually is coming as 2B into, I think, J plus 1, right? Centimeter inverse. Unit is very important. So did you understand how this thing has come, the selection rule?
Yes.
Okay, very good. So this is
But
one of
before that,
yes,
I have a question.
yes.
The that is M for in hydrogen is rotational quantum number. What is M here?
For a
Yeah.
rigid rotor, it is also a quantum number. So how can I tell you? So if suppose it is rotating, so it is also precessing. So suppose it is rotating like this. Okay. Suppose this is one of the planes. So I am showing how to think about the aim here. Okay, good question. So can we say that m is eventually the same thing as, suppose L square is, so L square operating on your wave function is giving you the orbital, the value of the orbital angular square of the angular momentum, right? Is J into J plus 1. So what will M gives you or LZ gives you. Can you tell me what will LZ give you? Suppose not on psi but on y theta phi. What will it give you? What do you think? What will it give you? Easy, right? For like hydrogen atom, it will give you M H cross this, right? So this is same. So this is also a magnetic quantum number. So actually, this will so from M actually. So what I was trying to say, suppose this is your z axis. Okay. Suppose it is rotating in here. So here the theta is I think 0, right? A 90 degree. Right. This is your mu, or this is your this is the what can I say? This is the position of your vector. Okay. Suppose mu or something. The position and the mu will have the similar direction. Suppose this is the angle. Then it is theta is equal to 90 degree here, right? So here your L is, or in this case it is J, right? So how to write this? J is 0, right? Or what is the value of J? No, I am making some mistake. Let me erase that part. Do I have a eraser option? Wait. Sorry. Okay, I have a eraser. I'll go to the next page and do this thing. I have, did I, as a joules, that what has gone. Let me write it like this. Okay. So what I was telling, that suppose this is the z axis and this is an angle your position is making. Suppose this is your r, or suppose here the mu naught, your the next thing that is going to come. So suppose this is your r or something like that. Okay, this vector. So this is making a theta angle in case of hydrogen atom. So this is giving you the so your L is also on the same, right? L orbital angular momentum, and L square is square of that, square of orbital angular momentum, and L is orbital angular momentum. So they actually give you the energy thing also, right? Am I saying it correctly? Or you can say L is going to give you the direction, I hope, and N, I think at last N quantum number in hydrogen atom will give you energy, right? There are three things. M, I think, is going to give you, I am making some mistakes, let me not go into that. And your LZ operator, that is your projection of L operator. L means orbital angular momentum, that will give you LZ, and that value is actually for a rigid rotor. Now for a rigid rotor, R is constant, so it is going to give you mh cross, and this is actually root over L in a, for a rigid rotor it is J into J plus 1 h cut. Okay, so actually it is equivalent to the magnetic quantum number, in hydrogen atom. So this is M, what we are talking. So in that is M, right? This is the equivalent quantum number, you can say. And M is actually going to give us the degeneracy in J, that you already know. The degeneracy is 2J plus 1, right? That has already been, I think, discussed in the class. So are you answered or are you confused? I am a little bit confused myself. What do you, so is it making sense, or what do you think?
Yeah, mm, a
So,
little bit confused and a little bit also.
so this is actually the magnetic quantum number, equivalent to the magnetic quantum number in hydrogen atom. So this will also give you the value of Lz, the projection of orbital angular momentum. M, this capital M, will also give you the projection on the Z axis of the orbital angular momentum, and L will give you, means L into L plus 1. So there are three quantum numbers in hydrogen atom, right? Each atom.
Yes,
So N gives you energy, L gives you, I think, the direction, okay, and I think M gives you the am I talking sense, or I think I am making some mistake. I think L gives you idea of the position, and M gives you the Lz, that is the projection on the projection of the orbital angular momentum in the Z axis. I think it's correct. N gives you the, so you know, right, that energy of the 1s depends on the N. So 1s, 2s have different energy, but 2s, 2p, they are degenerate until any magnetic or electric field is provided, right? So now, so that is one thing. So what I was discussing, so okay, so we are discussing of the selection rule, and this part I think I will try to give you some more data next time. So you have understood the selection rule, you have said, right?
yes.
Yes. So there are some, so they have used some recursion formula, but before that, what is the most important factor that one molecule should have to be rotation, means microwave active, something like that. So you will grade rotational spectroscopy, or you can do rotational spectroscopy of a molecule. So what is the essential criteria? So obviously the selection rule gives you selection rule, that is delta J plus minus 1, and for mu Z, that is direction, dipole moment along Z direction, I think that delta AM is 0, right? And for mu X and mu Y, I think delta M is plus minus 1. But eventually you will see that the main thing is delta J plus minus 1. And what do you think, what is the another very important parameter, physical property one molecule should have to be rotational active, rotational microwave active?
Polarity, permanent polarity.
Yes, permanent
Polarity
dipole
should be.
moment, right? That is, I think, mu naught. So to differentiate the reduced mass from a dipole moment, we are expressing it as a mu 0. Okay. So okay, now that you know, so now what are the other things, selection rules, so I will not go into that because you have understood that. One more thing, that is, so the selection rule will come from the transition moment integral, right? So transition moment integral is, so let me write the term once again, TMI, transition moment integral, that is in a bracket notation, it will be something final mu naught and psi I. So for a allowed transition, what do you see? The transition moment, what will be the value of transition moment integral? Should it be 0 for an allowed transition? What should be the value of TMI?
It should be not equal.
Yes, very good. It should be not equals to 0. So these things will be, I think, discussed in week 4 when the perturbation, light matter interaction will be discussed. So on the next lecture we will directly start from the week 4. Means there will be some misunderstanding because the quantum mechanics is going to involve, and we will discuss that on the next meeting. Okay, but before that, what else we have? We have one more thing regarding the population. So I will just write it for the sake of the formulas. Population. So acha, we will have some questions in the assignment too, so we will do that. But what do you think? So rotational lines or something like this. Rotational lines means the rotational energy levels. I am trying to say. So the energy gap increases, right? J equals to 0, J equals to 1, J equals to 2, 3 and 4. And this is the energy, right? So what is the energy of this level? 0, right? In centimeter inverse. For these levels it is 2b. For this it is 2 into 2 plus 1, right? This is 6b. Next 3 into 3 plus 1, that is 12b. And this is 4 into this is 20b, right? And it will increase for a non-rigid rotor, right? So what do you think, where is the maximum population? Is it in the ground state, means J equals to 0, or it could be higher, or means there are two options. If it is in J equals to 0 or J equals to 4 higher than J equals to 0, what do you think? Achha, before that, tell me what is the degeneracy we have already discussed, right? Because for each J there are 2J plus 1 M's, right? Huh? Means not
Yes.
right. So for suppose for then 1, actually there are 2 lines, something like that, okay, which have the same energy. Now for 2 it is 5, something like this. So your population is actually means varies as your degeneracy as well as a thing called Boltzmann distribution, right? That is minus delta E by KT. KT you all know, that is thermal energy, KBT, where K is Boltzmann constant. And I think I will not go into the thing. I think Sarah has shown for a maximum population, the population should be, the derivative of that should be 0 for a for J max or max population, max BJ, and it will be J max at which rotational state or rotational level the thing will be maximum will be given by KT by 2BAC minus half. So it will always depend upon the temperature, okay, and these factors. And it has been discussed that 10, so if you get an answer like 10.5, 10.2, it is the maximum possible integer, right? It will be 10. So if it is 10.8, it will answer is 11. So it is not like that your j equals to 0 has the highest population. This is the reason why this is the case, because there is a term degeneracy is attached with this. Okay, so if you don't have the degeneracy, how does it look like? So please have a thought on that. Means do a derivative where 2j plus 1 term is not there, and here you are taking the energy in joules again, right? So just remember that point. Okay, so now we can solve the, I think, assignment problems, assignment 2 problems, right? Let us go. So this is the week 2 assignment problem. So should I go into this, or do you have any other doubts from the classes?
No, no doubts.
Okay. So this will be a very quick one, I guess. Okay, so the spacing between the successive energy level of a rigid rotor. What do you think? We have already shown you the thing, right?
Mm.
It was something like this, close, something like this, right? So it is same, increases with increase in energy, or decreases
B
the and goes through a maximum.
increase, increases with increase in energy.
Yes, so this is correct. Now let me also write the thing. J equals to 0, it was 0. J equals to 1, it was 2b. J equals to 2, it was 4b. No, 6b. J equals to 3, it was 12b. Now the spectral lines you will get from here, right? These are your spectral lines. So you are only going to get delta E, right? Between j plus 1, delta j plus minus 1. So what would be the answer here? The spacing between two successive microwave spectral lines. Is it same? Increases with increase in energy, decreases in energy, or goes through a maximum? The spacing. So what
Spacing is same.
spacing is same, and what is the value?
2B.
2b, right? Yes, correct. 2b what? What is the unit?
Sorry?
2b what will be the unit?
Unit. Uh, unit is centimeter inverse.
Could it be joule also?
Yeah, it can be joule.
Yeah, it can be joules as well as centimeters. Just for the mathematic purpose, actually, what we are trying to do in rotational spectroscopy, most of the things are discussed in centimeter inverse. Okay, so just take a look on the questions always, huh? So to play with you, they can put the value of B in joules. Naturally, we will think it is in centimeters inverse, and we will do the math. So it can be in joules also. Okay, let it be. So the third question, it has to deal with the population, huh? Intensity of a microwave spectral lines is same. So four options are same. What do you think for the third question?
Goes through a maximum.
Goes through a maximum, and it will look like something like here. It depends on the thermal energy. So what will happen if so let me so this is your J and this is your intensity of the lights. Okay, so what will happen if you increase the temperature?
If we increase the temperature, then the J value where the intensity is maximum increases.
Yes, then actually you will see these lines to move, right, towards red shift, right? Is it correct? Because your J
It
max is
goes
going to change with increasing temperature.
blue.
blue shift.
Yeah, blue shift.
So if you increase your temperature, so your temperature you are increasing, so what do you get? That your J max is formula is not from the formula. So from means I am writing the formula here, but from the general knowledge also, common sense. So if you increase your temperature, so your J max is going to increase, right? Is it not?
Yes.
So then suppose you are getting something, this is for so the gaps are always 2b, so this is 0 to 1, suppose this is 0 to 1 and this was earlier it was 2 to 3. Okay, so this particular line what I am saying, now your maximum population has shifted from 2 to 4, right? Suppose what I am trying to say, suppose this is a T1, okay, and I am already writing T1 is less than T2. I will draw only 3 lines. So this is 0 to 1, this is 1 to 2, this is 2 to 3. Okay, so suppose your maximum population was in 1, so your maximum intensity you are getting from 1 to 2. Why so? Because your maximum population at 1, t equals to 1, your J max was in 1. Okay, so that's why you are getting a maximum intensity from 1 to 2. Your intensity depends on the population, right? Now suppose for a T2, this is J and these are intensity, right? So for T2 your J max suppose will increase, right? Suppose shifted to 2. So what do you expect? So is this step clear, that T2 being T2 greater than T1? Now
Yes.
at T1 the J max was 1, right? Now what do you think? If you increase the temperature, that is T2, your J max will increase.
Yes.
Now suppose it has went to 2, because 2 is more than 1, right? So now what do we expect? So intensity related to the second rotational level will increase because it has more population. So
Yes.
we are only talking about 0 to 1, 1 to 2, 2 to 3, not the reverse one. 1 to 0, 2 to 1, we are not talking about that. So we can expect that 0 to 1 will be something like that, 0 to 1 to 2 will decrease, but now your 2 to 3 will increase, right? Because your 2 has more population. So did you get this point, what I am trying to say?
Yes.
Okay, so with increasing the temperature, what you will see that your intensity of the spectral lines will have a rate shift. Rate shift means it will go to the right side. Rate shift is a wrong term to use here, but it will shift to the right side, right? I hope you have understood. So what about the next question? Question number 4. So that we have already, I think, discussed, right? Essential conditions for microwave activity is that the molecule must be linear, must be non-linear, have permanent dipole, lack permanent dipole. C, right?
Third one, common.
Yes, it should have some dipole moment. So in transition moment integral, you will see that the mu 0 part is there, that is a constant, but it will play a major role. First you have to have some dipole moment, then the selection rules will matter. Okay. So now the next question is, in the microwave spectrum of a molecule, in absence of any external electric or magnetic field can be used to determine what? So means
Bond.
bond length, right?
uh,
What about dipole moment? Suppose,
Dipole moment is should have to determine the bond length, right?
so it will come from the B, right? The rotational constant. So what is B?
Yes.
In centimeter inverse, B is 8 pi square mu r naught square C. C you know, H we know, 8 pi square we know. So we need to, so if we know the molecule, so this is not a dipole moment, right? So for confusion it will be like that. So this is your reduced mass, not the so that's why you can confuse with the dipole moment, right? So dipole moment you can't really know, right? You can only get the R0, that is the bond length. That you have yeah. I just wanted to confuse with you the dipole moment. Do you will you get the molecular mass?
Sorry?
Will you get the molecular mass?
No. No.
Why? If you
Molecular
already,
reduced mass we do.
so yeah, you will get the reduced mass, that is m1 m2 by m1 plus m2, but you will not know that which one is m1 or which one is m2 if you don't know your molecule. So if you already know your molecule, that you are using O2, with O2 you can't do, right? Rotational spectroscopy, you need HCl, or oh my god, I have given you the answer for the next question. Oh, let it, right? So molecular mass, if you already know the molecule, then you know the molecular mass. If you don't know the molecule, then you can't distinguish between m1 and m2 from mu to get the molecular mass. So molecular mass also you can't get dipole moment. And what about bond strength? What do you think? Where can we get the bond strength? For that you
So
need to,
bond,
tell me.
bond strength we can guess, for example, if the bond length is large, the length is large, so the bond strength will be less. So if the bond length is less, the bond strength will be
Very good,
more.
very
So
good. But that is a qualitative value, not a quantitative. So for quantitative bond strength, actually, you will see we have given a good answer, very good answer. But to get it quantitatively, you need to do micro IR spectroscopy. That is the vibrational spectroscopy. That is coming in the week 3. That is already there. So please read those three. I think three lectures are there, and I think the assignment you need to submit it by tomorrow. Okay, so that's why what I am going to do in the next week, that I will discuss week 4 next week, so that you can revise that thing. You will read that thing earlier, but you should get a revision from this lecture, and you will solve your assignment after that. Okay, let it be. So the bond state you will actually going to get from the IR spectroscopy, not from the IR spectroscopy. Okay, so there is going to be something known as what is force constant, something like that. Okay, in a bond. So that vibration of that bond will give you IR spectroscopy. Okay, so that you will read. Okay, now 6, question number 6. It's easy. Which of the following molecule will show microwave activity? So first, question 4 have a permanent dipole moment. So HCl will have a permanent dipole moment. But this is a MSQ question, right? From the square type thing you already know. What about H2 won't have? What about SF6? What is the structure of SF6?
octahedral.
Octahedral. So all the molecules are same. So eventually, the dipole moment is going to be 0, right? Permanent dipole
0.
moment. Yes. So it won't have. So what about CH3Cl? So this is not chloroform. The chloroform is CHCl3, right? So this is Cl. What is the structure? What do you think? What is the structure? CH
Tetrahedral.
tetrahedral, right? So what is the direction of dipole moment from in CH bonds?
Towards C.
Towards C, right? Yes, correct. And same from Cl, C to Cl, right? So overall it will point towards this. So if you check in Google, you will see it has a permanent dipole moment about 1.8 or 1.9 dBi. Okay. So it will also show microwave activity. So these two molecules. So we have, I think, one more question left. Okay. So that is a mathematical question. That's why I have kept it in the there. So for this question, what is given? The fast rotational absorption. So does it really important? It has to be the fast rotational absorption. So all the rotational spectra, these all have a gap of 2b, right? So does it has to be always fast rotational spectra or fast rotational absorption? It could be anything, right? What do you think? Am I confusing you? Okay, let us not do that. Okay, so it is given that the fast rotational absorption of 12CO, see this isotopic thing is coming, right? Is found to occur at this centimeter inverse, while that of XU, means another isotope of carbon is there, that will give you lesser rotational absorption. So we have to find the X. So it will be easy. So let us write these things. So you don't have to mark up, but eventually while doing this problem you will remember these things. Mu r naught square C centimeter inverse, right? See, we need to always play with this, and the fast rotational absorption is 2b, right? So factor of 2 is there, but so suppose this is my M1 molecule, this is my M2, or let me not write it that way. Achha, why I am writing it? This is M1, this is M1. So what do you think? What are the things going to be constant in terms of this rotational thing? Two podcast. So what is the things going to be constant in the rotational constant from 12CO to XCO? Avantika?
8 will be constant, pi square will be constant, C will be constant, and H log.
R0? What do you think?
R.
Actually, for mathematical reason, here we are going to, for easy calculation, we are going to take R0 to be same for both 12CO and XCO. Okay. So, okay, let us do that then. And one more thing. So, BM2 is what? For a second molecule. Then only this part is going to change. Mu M2 not square C. So we don't have to deal with these many terms. So what we will do, that Bm1 by Bm2 is going to be mu m2 by mu m1, right? All the other things will going to get cut. So actually this Bm1 is not this. The Bm1 is not this. This is 2Bm1 and this is 2Bm2, right? But as we are taking a ratio, that doesn't really matter. So this is going to be 3.8424 and divided by 3.6734. And what is mu m1? Mu m1 means mu 12CO. Can you tell me? It will be, and what is the atomic mass for oxygen? That is 16, right? It is m1 m2 means 12 into 16 by 12 plus 16, right? That is, I don't want to do that. So eventually your mu m2 is 3.8424 3.6734 into mu m1, right? That is 12 into 16 by 28. I will not do this, but can you guess the answer? What is going to come, or did you solve it?
Answer is 13.
Answer is 13. So anyway, you could have tell me that there is another isotope of carbon is 13. For a MCQ question, this is obviously there are other abundance. I think 14 is there. Is it there? 14C. 14C is there, right? I think it is a for aging and other thing. What carbon is used? 14C, right? I think so. 14C is used for the radioactive or that aging thing.
Carbon dating and
Carbon dating, yeah, 14C. Yeah, so the case would have been wrong also. So yeah, actually you are going to be getting something around 13. 13 is actually the correct answer. So here you understand two things, that R0 is going to be the same, and one more thing. So from this question, let me tell you. So when your mu radius, suppose this was your earlier thing, right? That this is your energy levels, okay? So this is your 0, then 2B, then 6B, then 12 is it? 3 into 4, yeah, then 20B. And so suppose this is for mu, this is for 12C. So and energy is what we already know. Energy is, or EJ is B into Bj into J plus 1 centimeter inverse. Okay. So what do we expect for 13C? How the energy levels are going to be from this question? Means I am not asking you in general. What do you think is going to be the energy levels? Can you guess?
can you repeat the question?
Yeah, so what I was saying, that suppose this is the energy level for 12CO. Okay. So this is just think this is the energy level of the 12CO rotational levels. Okay. For J equals to 1, J equals to 2, 3, 4 and 5. So my question is, what do we expect for 13 CO? Means the energy levels. Will it be same? Will it increase? Will it decrease? What do you think? And you can have your answer from this question itself. Okay. So I am giving you that hint. So you can think for 1 and 2 minutes, or you can give me answer right now if you wish. So for 13 CO, what should
B
we? Yes,
B will be less for
B will,
13.
yes, very good. B will be less. Then what will happen to the energies? You are correct. You are correct. You are going on a correct path. So if you go from 12 CO to 13 CO, your B is going to be decreased, right? So then what will happen to your energies, energy levels? Your energy is B into J plus 1. Right? Suppose this is for
Energy will be less.
will be less, yes. So energy level of 5 will be something here, 12 will be something here, 6 will be something here, 2 will be something here, and 0 is 0. There is no change in 0, right? And 2B there is some decrease, 6B there is some decrease. I hope you at least got something new from this thing, right? At least one. Yes. Okay. So similar, I think similar. So Sarah, I think also discussed about. So these are all about non-rigid rotor, right? But in real life, can it be anything non-rigid? Means we are talking about atomic bond length or something like this. Suppose when it will go to higher and higher energy levels, means it is, what does rotational energy means? Higher rotational energy means, so it is rotating with high rotational energy, right? Means it is rotating fast, right? So at certain level of means at certain point, the bond is going to bond length is going to change. Okay, there this non-rigidity doesn't really hold. Then the rigid rotor thing comes, and these are all for rigid rotors. I am very sorry. These are all for rigid rotors, right? The bond length is constant. Now, after a certain energy, rotational energy levels, you are going to see that nothing is really rigid. Then bond length can change. Then it will come that something around non-rigid rotor, and where the R can vary. Okay, there actually the energy for rigid rotor is this, and here you are going to see another term that is known as, that is known as, let it like d into, I think, j square. It is j plus 1 square. I may be wrong. Just please check with the lecture notes. I may be wrong. That the d is known as, say, fast order correction, something like that. Okay, so this is coming due to centrifugal distortion. Means at higher energy levels it is rotating, right? High energy, then some due to that there will be change in bond length. Okay, so this will be there. D is another constant, and this is all coming for a non-rigid rotor. You can read Banwell's book. Okay, Banwell. So this is actually, I should not say, but it is available online. Why I should not say? Because there are issue of licensing and other things. You can find it. I cannot really. Do you have Banwell's book?
Okay, sir. Yes, sir. I have it
Great.
online. A soft copy of it.
Okay, great. So you can read it from there. Rotational spectroscopy is, I think, it is discussed very well there. These are the things are there already mentioned. What will be the effect of mu, change in mu? What is going to be the effect of non-rigidity, means on the energy levels? What is going to be the effect of non-rigidity? These all the things are being discussed there very nicely. Okay, so I don't think there is any more slides there, but we have time. We still have time up to 8. So if you want to discuss anything, means molecular spectroscopy regarding this, or so we can discuss. If acha, let me close the slides once again and stop. Okay. So do you have any other queries, questions, or something like that? Any doubts? So the aim, what you have already asked me, that the what is aim really matter? Aim really means in non-rigid rotor. It is just an same thing. It will give you, provide you the Z projection, projection of the orbital angular momentum on the Z axis. So it is equivalent to your magnetic quantum number in hydrogen atom.
Okay, sir.
We can think. I think it is also mentioned in Banwell's book. Also, you can check it. And that degeneracy is coming due to this 2j plus 1, because there are m number of states and they all have similar energies. Now, in case of some external magnetic field or electric field, they can get separated. They may get separated, and then it will be problematic. I think one more thing was discussed in the class, that effect of mu in suppose we are taking some molecule from market, right? So have you done any lab work? Means MSc so you are in your first year MSc, right?
Yes.
So in BSc level, have you done any laboratory reaction or something like that? Anything? Organic reaction or any synthesis? Anything? Lab work? Means I am asking you because you may be may read it during the lockdown period. You may not have been able to go to labs. Was it something like that? Means did you perform some laboratory experiments? Why I am asking you? Have you seen some chemical bottles, something like that?
Yes.
Yes.
So,
Yes. So actually the isotopes are not really. Suppose you are using some anthracene or something organic molecules. The isotopes effect means those are not all carbons are 12 carbons, right? That's why we are getting NMR spectra, proton NMR spectra, right? 1H. Sorry, 13 carbon, 13C. Actually, all carbons are 12C, right? But what we are doing in NMR, 13C. So all the carbons are not really of same isotopes. So that's why what I am trying to say, in rotational spectroscopy, if you increase the resolution as sir has discussed. Instead of one line, you may see 2 or 3 lines, and that will come because of different mues, right? Different mues, and different mu means different isotopes, right? And from that you will get bond length. And if you have a very high resolution this spectrophotometer for rotational spectroscopy, you will get the isotopic abundance from the intensity of those two or three lines also, right? So this is also very important. What are the advantages of rotational spectroscopy? One is bond length, second is this isotopic abundance you can get. So these are the type of question that can come in it's not only in this course. You may opt for CSIR, NET, GATE, whatever. So there these kind of questions are very common. I think related to this rotational constant, I think there used to be one question at least, right? I hope you have seen or not. You will get some. This question is very common regarding this 2b centimeter inverse, the gap between the rotation. So I hope you can solve these questions further, right? And if you have no other question, then we can stop it now and we can join in the next week. Okay? And till then, I will surely share with you the CVEC effect if I have any document. So did you read it yourself, or do I really need to send any document regarding that? The CVEC effect means if you have two different semiconductors, and if you at the two joints you provide two kind of heat, means one is heated, another is cold, means you create two kind of temperature, then actually there will be a voltage difference between 2 points, and current will means there will be a voltage difference. That is actually a CVEC effect. I think the Peltier effect is the reverse of this. If you apply some current, then there will be temperature difference, right? And do you know this?
Yes, sir.
Okay. So if I get some document, I will share, and till then we can stop it here and meet next day. Thank you for joining.
Thank you, sir.